We are going to go over practice questions from electrochemistry, thermochemistry, and also chemical kinetics. First question: in not more than three sentences, explain what is meant by enthalpy is a state function. Now, we know that a state function is a property that depends on the system's past but not on the current state. Okay. For example, when you've got a hill like this, when you get to throw a ball, it doesn't matter where you are. If you want a ball to reach this height, so the height is always counted from the very beginning of the hill. So the height is the same that is going to be covered whether you throw a ball in this direction or you throw it straight like this, it will be the same. So altitude is an example of a state function. Now a state function is simply a property that does not depend on the system's past but only on the current state. An example that you can give is enthalpy. So just from the equation, we know that change in enthalpy is equal to change in internal energy plus pressure times volume. So all the things we are saying in this equation are all state functions. The internal energy, pressure, volume, and also enthalpy, all of them are examples of state functions. Now, B, if 356 joules of work is done by the system. Now, it is the system which is doing work by. And so on the system's point of view, when the system is doing work, work is always negative. Okay, so if 356 joules of work is done by the system to the surrounding, while it loses and there is also a loss in heat to the environment, what is the value of the internal energy? Now the change in internal energy is given as heat plus work, and the heat, because the heat is being released by the system, and so we can see they are negative 298. It's going to be negative because it's being released, plus work. It is the work which is the system is doing work on the surroundings. So whenever the system is doing work, work is always negative. And so that is going to give us negative 645 joules. That is going to be the internal energy. A chemist returned 10 students dropped 50 grams of unknown metal at 100 degrees Celsius into an insulated vessel containing 100 milliliters of water at 25 degrees Celsius. What is the specific heat capacity of the metal if the final temperature of the combined metal to water system is 30 degrees and the specific heat capacity for water is 4.18 joules per gram degree Celsius? Now when you get something that is hot, you drop it in water which is cold. So in this case, this is the heat of the metal which is going to be lost is going to be equal to the heat of the water that is going to be gained. So whenever you get something that is hot, you drop it in something that is cold, in a solution that is cold. The hot thing gets to release some heat, and the heat that is going to be released, we're going to indicate with the negative. It's going to be equal to the heat that is going to be gained. The other one is going to gain, so the heat is going to be positive. And in this case, it's the metal which is hot because it is at 100 degrees, but final temperature for both of them is 30. So we can see that the temperature drops from 100 to 30. Whereas the water, the temperature is at 25, but the final is at 30. There is an increase there. And how do we get to find the heat? Heat is given by mass times the specific heat capacity times change in temperature, and they should be equal to also mass times specific heat capacity times the change in temperature, but this side is for water, and so here to be negative the mass of the metal 50 grams, specific heat capacity of the metal, that is what we want to find, and then the change in temperature. The final temperature is 30. The initial for the metal was 100. This is in degrees Celsius, and this should be equal to the mass. Okay, we've been told it's dropped in an insulated containing 100 milliliters, that is 100 grams of water. We know the density of water is 1 gram per milliliter, so if the volume is 100 milliliters, even the mass is going to be the same. So that is 100 grams. Specific capacity of the water is 4.184 joules per gram degree Celsius. Now the change in temperature. The final temperature is 30. The initial for water was 25. This is in degrees Celsius. Now from this we can see that the gram which is here will cancel out with the gram there. The degree Celsius cancels with the degree Celsius there. So what you are going to get, if we get to subtract 30 minus 100, that is going to give us negative 70. And negative 70 times negative 50, that is going to be 3,500. And then we have got C here. And then we have got the units which have remained, grams and degree Celsius. And this is going to be equal to, if we get to multiply 30 minus 25 is a 5, 5 times 100, that is a 50, 50 times 4.184, that is going to give us 2092. The only thing that is remaining, the unit there, is a joule. So I'm going to put a joule there. So for us to be able to find the value for C, we are going to divide by 3,500 grams degree Celsius. Even the other side, 3,500 grams degree Celsius. So this cancels with that, grams degree Celsius cancel. So we are going to remain with C, and that we can see is going to be in joules per gram degree Celsius. And so 2092 divided by 3,500, that will give us about 0.5977 joules per gram degree Celsius. Then that is going to be the answer. Question number 3. Calculate the carbon to carbon bond energy in ethene using the data below. Now we've been given this equation. Ethene reacts with hydrogen to form ethane. Now we need to visualize how these bonds are in this compound. We have got first carbon double bonded to carbon. Now this carbon has got two hydrogen attached, so there's one hydrogen there, there's one hydrogen there. Same with the other carbon, one hydrogen and then the other hydrogen, and this is reacting with hydrogen which has got H, which can be written also like that, and this is forming ethane. Ethane has got a single bond, and then there's hydrogen, another hydrogen, and then also hydrogen, and then another hydrogen. So we're going to break this. We can see there's a carbon to carbon double bond here, and then we have got a carbon to hydrogen, and there are 1, 2, 3 and 4. So carbon to hydrogen, there are the 4 of them. And then we have got just hydrogen to hydrogen on the reactants. And this is giving us, on the product, we have got a carbon to carbon double bond, I mean single bond there. And then we have got carbon to hydrogen 1, 2, 3, 4, 5 and 6. So we have got 6 carbon to hydrogen bonds. Now we've been told that the enthalpy for this reaction is that value. And how do we get to calculate the bond energy when you are the enthalpy using bond energies? For us to break these bonds, in other words, for us to form this, the first thing, we need to break the bonds on the reactants, and breaking of bonds requires energy, and so we are going to be putting energy. The formation of a bond releases energy, so on the product, energy is going to be released, and so the enthalpy of the reaction using bond energies is equal to the sum of the heat energies of the reactants, because they require energy. Energy is positive, while for the products, energy is going to be released, and so that's why it is negative, the heat energy of the product. Now the enthalpy is already given at negative 138 kilojoules per mole, and this is going to be equal to, on the reactants, what are the enthalpies on the reactants? We have got a carbon to carbon double bond, and then plus we have got 4 carbon to hydrogen, and carbon to hydrogen, the enthalpy, the bond energy is therefore 12 kilojoules per mole, and then we have got hydrogen to hydrogen, the bond energy is 436. So this is all on the reactants. And then on the products, minus, on the products we've got carbon to carbon, that is a 348, and then plus we have got carbon to hydrogen, that is 412. but we are multiplying this one by 6, so don't need to forget that. So by 6 there. So just go on and punch this on the calculator. We have got negative 138 is equal to carbon to carbon, and then 4 multiplied by 412, and then plus 436. That is giving me 2084. And then this side we're also going to compute that. We have got 348 plus 6 multiplied by 412. So that is negative 2820. So if we subtract 2084 minus 2820, we are going to get negative 736. That negative 736, taking it the other side, it will give us negative 138. It becomes positive 736, and that is going to be equal to carbon to carbon and bond energy. So 736, we have got negative 138 plus 736. That is giving us 598. So that is going to be it. It is in kilojoules per mole. That is the answer then for this one. Question 4. The enthalpy change for the reaction below is 543 kilojoules per mole. This is the reaction. Okay, the enthalpy change for the whole reaction is given already, and it is a positive value. Now, question A. The reaction above is dashed, and therefore heat is dashed by the reaction. The reaction above, the only way the enthalpy is positive, the reaction is endothermic. Whenever the enthalpy is positive, the reaction then is endothermic. It takes in heat, and therefore heat is absorbed. It is absorbed or taken in, whatsoever way that you can use to mean the heat is going to be found on the reactant side. Now for B, given that the enthalpy of formation for this compound, now we've already been given the reaction. This is the same question. 2 POCl3, this is breaking to PCl3 plus oxygen. We need to make sure that the reaction is balanced. Is this reaction even balanced? So there should be a 3 on the oxygen here, so that this times this, that is giving us, I think it is okay. Okay, there, yeah. Unless putting a 2 here, then it will be balanced, because we need to have 2 phosphorus just as we have here. Apart from that, we need to have 6 chlorine atoms, and those are the ones. 2 times 3 there, that will give us 6. Oxygen are just supposed to be the 2 of them, just like we have 2 there, so just a 2 there, then it is balanced. Now we've been given that the heat of formation for this compound, which one is this? This one, which is here, negative 558.4 kilojoules per mole. Now I want to calculate the heat of formation of this one. What would be the heat of formation, delta H of formation? But we know that the whole of this reaction, the heat of this reaction is positive 543. How do we get to find the heat of formation for the other one? Well, the enthalpy for the reaction is equal to the sum of the heats of formation on the products. When you are using bond energy, it is the reactant minus product. But when you are using heats of formation, it is products minus reactants. So we need to get to differentiate that. Now the heat of formation, the heat of a reaction is already given as 543, and this is equal to the heat of formation of the products. We've got oxygen. For a pure element or a diatomic gas, the heat of formation is always 0. And then plus we have got 2 of this compound. The heat of formation of that one, we don't know. That is what we are trying to look for. From this, we are going to remove the heat of formation on the reactant, and then we have got 2 of these, and the heat of formation is negative 558.48. I left out 1 8 there when writing. Now this is going to give us 543 being equal to 2 the heat of formation, and then Let's get to multiply 2 times 558.48. But this is a negative and this is also negative, so that is going to become positive here. Positive 1116.96. I'll take this value the other side. So that will give me 2 enthalpy of formation being equal to 543 minus 1116.96. So this will give us a change in heat of formation being equal to 543 minus 1116.96, and then that answer that we get, we're going to divide by a 2. So that is giving me negative 286.98. This is going to be in kilojoules per mole, just as all other values are in kilojoules per mole. So then that is going to be the answer for this question. Question number 5. This is on chemical kinetics. The decomposition of 0.5 molar hydrogen peroxide gets to decompose into hydrogen gas and also oxygen gas. Of course, this is also a gas. And we've been told the rate constant K is equal to 1.925 by 10 to the power, it's all supposed to be to the power negative 3. Okay, negative 3 second to the power negative 1 at 313.15 Kelvin. Determine the time it will take for 80% of the original concentration of hydrogen peroxide to decompose. Now, just looking at the unit of the rate constant per second, we can tell this is a first order reaction. And for the first order reaction, the integrated rate law is natural log of A, or the concentration at a certain time, is equal to negative kT plus the natural log of the initial concentration. Now, we want to determine the time it will take for 80% of the original concentration of hydrogen peroxide to decompose. The initial concentration will be given as 0.5. Now, if 80% gets to decompose, what percentage remains? We can easily tell that a 20% is going to remain. So we want to find what is remaining. So what is remaining is 20%, and 20% is 20 out of 100. It's 20% of the initial, and the initial was 0.500. And this is going to give us 0.100 molar. Okay, so that is going to be the initial. The final concentration which remains after a decomposition of 80%. Let me just punch that again. 20 divided by 100 multiplied by 0.5. That is 0.1. Yes. So this is the concentration that remains. So natural log, we are going to put that concentration 0.100, and that should be equal to negative K, which is the rate constant, 1.925 multiplied by 10 to the power negative 3, and then times time. We want to find the time for which this is going to remain, plus natural log. The initial concentration is 0.500. Now I can take this value, which is negative, the other side, and then I can take this value the other side of the equation. So taking it the other side becomes positive 1.925 times 10 to the power negative 3t, and that will be equal to natural log of 0.500 minus natural log of 0.100. From our logs, we know that if we've got two logs subtracting, having the same base, we can divide the terms. So therefore, time is simply going to be equal to natural log. I'm going to divide 0.500 by 0.1 because they are the same they are same logs in the same base. And then this which I get, I'm going to divide by this term for me to remain with only the term. So divided by 1.925 multiplied by 10 to the power negative 3, and therefore the time is going to give us about 836 seconds. Question number 6. When a 6.50 gram sample of solid sodium hydroxide dissolves in 100 grams of water, so we have got this solid sodium hydroxide, it gets to disassociate in water. Is going to form sodium plus in aqueous and also hydroxide ions in aqueous. Now this reaction is releasing some heat, and the temperature rises from this value which is here to this value there. Now I want to calculate the change in enthalpy in kilojoules per mole of sodium hydroxide or for the solution process. Assuming the specific capacity of the solution is formed is 4.18. In other words, the solution is more of water. That's why we're using the specific capacity for water. Now again, the heat which this reaction is going to release is going to be equal to the heat which the solution is going to gain. Now the solution has got a positive heat, whilst the reaction, let me put reaction here, reaction has got a negative. Why? Because it's the reaction which is releasing heat by its decomposition. And how do we get to find the heat of the, so I'll say heat of the reaction is equal to negative heat of the solution if we divide both sides by negative. And how do we get the heat of the solution? Heat of the solution is simply given by mass times the specific capacity of the solution times the change in temperature for the solution. And this will be equal to negative the mass of the solution. We have got 100 grams of water, so that is 100 grams multiplied by the specific capacity for the solution, that is 4.18 joules per gram Kelvin, and then multiplied by the change in temperature. So the change in temperature, the initial temperature that you've been given is 37.8. Okay, no, this is the final, supposed to be final minus initial. And then the initial one we have been given is 21.6. Of course, these values are given in degrees Celsius, but this value which is here, the temperature, is in Kelvin. All we need to get is that when you subtract two temperatures in Kelvin, the change in temperature is going to be the same as the change in temperature when you are using degrees. So it's the same. If you convert this to Kelvin, and then subtract them, you are going to find the same answer if you go direct. So I'll just put a Kelvin here for the sake of cancellation of units, so we see what remains. Gram cancels Kelvin, and Kelvin also cancels out. And so this is going to give us, so that would be 677 1.6 joules. It's going to be a negative because of this negative which is here. So this is the heat of the reaction. This is the heat that is going to be released by the decomposition of sodium hydroxide. Now we want to give the unit in kilojoules per mole of sodium hydroxide, and we want to find the enthalpy. Well, we know that for a constant pressure calorimeter, the heat of the reaction is equal to the change in enthalpy, and therefore the change in enthalpy is also going to be equal to negative 6771.6 joules. Now I want to have the answer in kilojoules per mole. First, where am I going to get the mole? I need to find the moles of sodium hydroxide, which we've got 6.5 grams of sodium hydroxide as the one which has broken down, decomposed. So the number of moles is going to be equal to mass divided by the molar mass, and the mass for sodium hydroxide, that is 6.50, divided by the molar mass for sodium hydroxide, that is about 39.99711, and this is going to give us about 0.16251171 moles. Therefore, for me to find joule per mole, I'll just divide this answer by the number of moles, which is 0.162511 moles. And so this is going to be equal to, okay, before I even get to find the final answer, I want it to be in kilojoules per mole. Here we are seeing that the answer is going to be in joules per mole, but I want kilo, so I multiply. I know that I've got a joule on top, so I'm going to take a joule down. I want a kilojoule on top. But we know that in 1 kilojoule we have got 1,000 joules. So this joule and this joule is going to cancel out. So our unit is going to remain now in kilojoules per mole. And if we get to punch this, we're going to find negative 41.7 kilojoules per mole. then that is going to be our solution. Question number 7. What is meant by disproportionation? Well, we can see this is electrochemistry. Disproportionation in electrochemistry. Now, disproportionation is simply a redox reaction which involves simultaneous reduction and oxidation of atoms of the same element. So, it is simply a redox reaction involving the spontaneous or simultaneous reduction and oxidation of metal. So if this one gets to lose an electron, what does it form? Let me say it is M2 plus. When it gets to lose an electron, what it becomes, if it loses another electron, it becomes more positive. Now if it gains electrons, it will become, if it gains 2 electrons, it will just become M, neutral. Because gaining of electrons, the charge decreases. So this is called a disproportionation reaction because it is showing us the simultaneous oxidation and reduction of metal. Going in this direction, there is oxidation. Going in this direction, there is a reduction. So that is what is called disproportionation. Now, use the following to deduce whether magnesium oxide will disproportionate in acidic solution. So our interest is on magnesium, that's not magnesium, manganese oxide. So that is our main point. I'll put it on the middle here. Now, what happens when this compound loses electrons? We can see that, okay, look at this reaction which is here. If I get to swap this reaction, it's going to become manganese oxide forming. Of course, there is also hydrogen, but my interest is not more on hydrogen. I'm interested in this one. Manganese oxide is going to form manganese O4 minus and also 4 hydrogen ions and also 3 electrons. So I'm more interested in this compound and in this compound. These we can just put them there when we are balancing. Okay. So the disproportionation of this compound, we can see it is going into, when it loses electrons, 3 electrons. Let me just write this properly because we need to get to understand what's happening here. Let me write it here. So I'm saying Mn O4 minus plus 3 electrons. I'm only interested in this compound that has got Mn in it. Mn. I could have written everything. This is going to Mn O2. And then I'm going to write also the other side. I'm only interested in this one and the Mn2 plus. Mn O2 plus 2 electrons. And this is going into Mn2 plus. Okay. Now that we have got these reactions, I need to make sure that the Mn, my point of interest is here. I need to make sure that this is joining these 2 reactions. This one reaction and also this reaction. And how am I able to do that? This should be an intermediate, should be on the middle. That's my interest. Okay. So we can see that this compound which is here, let me write it now on this point, manganese oxide, like that. So I'm going to put an arrow in this direction. I'm also going to put an arrow in this direction. So we can see that this going in this direction, it is forming manganese 2 plus. And this same compound which is here going in this direction, where is it going? It is going into manganese O4 minus there. Okay, now that we have got this, what is the cell potential going in this direction? So the cell potential going in the other direction where we've got Mn2 plus is there. It is positive 1.23 volts. And then the cell potential going in the other direction, in the opposite direction, is here, 1.70 volts. Well, I haven't changed any sign here. Why have I not changed any sign? Because whenever this wants to disproportionate going in this direction, we can see that my putting of the arrow is going to affect a lot of things. The arrow is not supposed to be in this direction. I hope some of us who are watching can confirm that it is this one which is disproportionating. If I want to put the arrow in this direction, then I have to reverse the sign of this one. We can see where the arrow is going. It's going towards the manganese O2. So if I get to reverse the arrow, the cell potential changes. That is it. Okay, so that is the direction of the arrow, and the cell potential is now positive 1.70 volts. Now when you look at this compound, for it to disproportionate, we are going to compare the cell potentials on the right and on the left. Look at this cell potential here, and also look at this cell potential. Since the cell potential on the right, which we can see this one here, is smaller than the cell potential on the left, which is here, then magnesium oxide will not disproportionate. Okay, that is the statement. Whenever this cell potential which is here is smaller than this cell potential, there will be no disproportionation happening. Unless if this cell potential is much bigger than this cell potential, then there will be disproportionation. I mentioned that again. When this cell potential is bigger than this cell potential, there's going to be disproportionation. But when this one is smaller than this one, there will be no disproportionation. All right. Now let's look at this question. The compound hydrazine N2H4 is a liquid which is used in rockets. Some bond enthalpies are given in the table below. Calculate the enthalpy change for the oxidation of hydrazine using the enthalpy values in the table. So the reaction given is here. We can, whenever we are using bond energies, we should be able to understand the Lewis structures of the compound. N2H4 is like that. There is H here, there is H, another H, another H, and then there is oxygen double bonded to another oxygen, and this produces the nitrogen. There is a triple bond between each nitrogen, and then plus two water molecules. And so we have got one NH bond here, and then we have got 1, 2, 3, 4 N2H bonds. And then we have got oxygen to oxygen double bond. On the products we have got nitrogen to nitrogen double bond, triple bond, and then we have got OH1, OH2, and then times these two, that will be 4 OH bonds. So we have got 4 O to H bonds. Now calculate the enthalpy of oxidation. Therefore, change in enthalpy for the oxidation of this reaction is going to be equal to the enthalpy on the reactant. So we get the N to H double bond, which is here 158, plus we have got 4 times the N to H is here, that is 391, and then we have got oxygen to oxygen double bond, that is 498, and that is producing, sorry, it's not producing. If we get for the products, I mean for the reactants, now we are going to remove for the product. Enthalpy, I already wrote the formula for the first question which we did, is sum of the heats on the reactants minus sum of the heats on the products, and so minus N triple bond, the enthalpy, the bond energy is 945, and then plus 4 O to H is 464. So just get to punch this on the calculator, the value that we find. So 158 plus 4 multiplied by 391, and then plus 498, that is 2220, minus 945 plus 4 multiplied by 464, that is 2801. So 2220 subtract 2801, that is negative 581. The enthalpies have been given in kilojoules per mole, so even the value here is going to be in kilojoules. Okay, I think this one will just be in kilojoules. That is because we are multiplying by the number of moles. An example that I can just give here is, let's look at just this compound here. When you, okay, let me use this one. We have got, how many moles of water are here? 2 moles. And then you are multiplying by the bond enthalpy, which is in kilojoules per mole. So every time the mole here and the mole there is cancelling out, so I just remain with kilojoules. What are the units of the rate constant for the following reaction? This reaction given, we can see that it is K a to the power 2. Now whenever we can see by the power 2 that this is a second order reaction, unit of the rate constant is always given by molarity to the power 1 minus the order of the reaction and then time to the power negative 1. So this will be molarity to the power 1 minus its order is 2, time to the power negative 1. Therefore the unit is molarity to the power negative 1, time to the power negative 1. Whatsoever the time here, if it is in minutes, then we'll put minutes. If it's in seconds, we'll put seconds. Years, weeks, months, just like that. Calculate the rate at which nitrogen N2O2 is formed in the reaction at a moment of time when NO2 is being consumed at a rate of 0.05. Now, this is the reaction. Let me just rewrite it. 2NO2 decomposing into N2O2. Now, the rate of disappearance of NO divided by the coefficient should be equal to the rate of appearance of N2O2 divided by the coefficient. Now, if we want to calculate the rate of this one, we know the rate of this one. So the rate of N2O2 is what we want. The rate of this one is what has been given as 0.0592. So just divide that by 2 and that will give you the rate of N2O2. So just dividing that value by 2, this is going to give you the rate being equal to 0.0296. The unit is the same, mole per decimeter cubed per second. So this is going to be the rate at which this one is being formed. And the last practice question here, phosphine decomposes as shown. We have got 4PH3 producing P4 plus 6 hydrogen. This reaction takes place at 100 degrees Celsius and the rate constant is 0.372. What is the rate constant at 70 degrees Celsius if the activation energy is 73.2 kilojoules per mole? Now, what is the first temperature? Temperature 1, they've told us it is at 100 degrees Celsius. Convert to Kelvin, add 273. This is going to be 373 Kelvin. What is the first rate constant? K1, that is 0.372 per minute. Now, what is the second temperature? Second temperature is 70. Convert to Kelvin, add 273. And that is going to give us 343 Kelvin. Now, K2, let me even do this. It's the same thing. I just want to use T1. We have got 100. Let me use 273.15. It's fine if you use 273. I don't want to use 273.15. That is going to give us 373.15 Kelvin. And then K1, the first rate constant is 0.372 per minute. And then the second temperature is given as 70. We also add 273.15. That is going to give us 343.15 Kelvin. We don't know the second rate constant K2, but what we know is the activation energy, which is 73.2 kilojoules per mole. But when we are using this, it shouldn't be in kilojoules per mole. So we need to convert it to joules per mole. So we have got 73.2 kilojoules per mole. We are going to multiply. We have got a kilo on top, so we're going to put a kilo down, kilojoule, and then just a joule on top. We know that in 1 kilojoule we've got 1,000 joules, and so this is going to give us 73,200. Okay, 73,200 joules per mole. That is going to be it. All right. Now, let's get to progress. What are we going to do for us to find the answer here? We're going to use the Arrhenius equation. Natural log of K2 divided by K1 is equal to activation energy divided by the universal gas constant multiplied by 1 over T1 minus 1 over T2. Well, what we start with here, if we start with K2, we are going to end with T2. If we started with K1, we would have ended with T1. So this is going to give us natural log. K2, the second rate constant, is what we are trying to find. K1 is 0.372. And the activation energy here, 73,200 divided by universal gas constant that we use here is 8.3145. Multiplied by 1 over the first temperature is a 373.15. Subtract the second temperature, which is 343.15. This will give us natural log of K2 divided by 0.372 being equal to 73,200 divided by 8.3145. And then we are going to merge this as a single fraction. All you do is get your calculator, write 1 over this minus 1 over this. So the answer that I found after dividing this, I'm going to multiply that by 1 divided by 373.15 minus 1 divided by 343.15. It is giving me negative 2.062665235. If I want, this is a log. Whenever I've got a log, natural log of x is equal to 2. The base of this natural log is e. That means x is equal to e to the power 2. So even here, this thing which is here, k divided by 0.372 is going to be equal to e to the power negative 2.062665235. And so this will give us K2 being equal to do away with what is in the denominator here, I'm going to multiply 0.372 multiplied by e to the power negative 2.062665235. So that is e to the power that. Well, when you are punching on a calculator, just punch shift. There's a function which talks about natural logs. So just punch shift natural log, it will bring e. And just type your number, don't put a power. So this value that I found, I multiply by 0.372, and that is given me 0.0472866678. We can see this was given to 3 significant figures. We can also give this to 3 significant figures, 0.04 0.73. This will be also in per minute. Now the rate constant has decreased because the temperature reduced. Thank you so much for being present. Hope that was helpful.